Okay, so what we want to do is we want to look at vectors, and we've been doing a little bit of this, but now we're going to have a session where we're just really focusing in on this. And the idea is that when we are wanting to look at a resultant vector, we need to understand that we are creating an addition of multiple vectors. So with this example, like we've done before, we start in one place and end at another, okay? We're going to have one vector here that goes this far up. We're going to have another vector here that goes this far over, okay? And when I add the two vectors, so this vector plus that vector, I get a new vector, the resultant vector, this one right here, okay? And that is my resultant vector. And if I'm looking at displacement, again, displacement is a vector, okay, where it's d. Remember, the arrow means vector. That displacement vector is a resultant vector of these two vectors added together. So, again, a vector is made up of two things, a magnitude and a direction. So magnitude and a direction. So again, if I went 3 meters up and 7 meters over, I should be able to figure out the magnitude of this line and its direction. Remember again, I can figure out this magnitude because I can just use the Pythagorean theorem. A squared plus b squared equals c squared, where this is a and that's b, or vice versa. It really doesn't matter. But this is c. So in this case, I have 3 squared plus 7 squared equals c squared, which means it's 9 plus 49 equals c squared. So if I look at that and I say 9 plus 49, okay, is 58. 58 equals c squared. So c equals the square root of 58, which is square root 7.62. And again, c equals 7.62 with the units of meters. So that's my distance, right? That's this guy. So really it's 7.62 meters with a direction. Now when we talk about direction, what we mean is we need to know the direction relative to something. And right now, there's nothing giving us a relationship to. There's no point in which we're referencing from. So if we assume that we started at an origin of an xy curve, okay, where this is our x and this is our y, okay, where the positive y, the up in y is positive and to the right in x is positive, and down in y is negative, and to the left is negative, we can assume that we could get to this resultant vector from two different directions. We can get there from the x-axis, or we can get there from the y-axis. And what I mean is that if I am pointed in this direction, okay, this is the way I'm pointing, all right, then in order to get to the direction of the resultant vector, I would turn from the x-axis that amount of angle, so that I'm pointing down towards the orange. I could also have been pointing up, right? Again, pointing straight up, and then I'd have to rotate this way, clockwise, to get to the orange position. And if you've got, going to the right, we're going to go from the y-axis to the resultant vector. And again, doing that, we're going to go to the right from the y-axis. The resultant vector is clockwise, which is a negative number. And when we look at going from the x-axis to the resultant vector, it's going counterclockwise. And why this is important is that when we think about that, we actually have a standard that says, okay, anything going this direction, which is counterclockwise, is positive, and anything going that direction is negative. So what I want you to do right now is and we'll do one. Let me finish this up, and then I'll have you do your own. What we'll do is then we'll figure out what the angle is. Now we can measure this angle two ways. Well, again, one from the x-axis, so I can say theta 1 maybe. And again, the naming is irrelevant. It doesn't really matter. You can call this theta 1, theta 2, of course, theta pink elephant. Or you can say, well, look, here's my theta 2, and it's from here to here. So theta 1 is from the x-axis to the orange vector, and that would be what sign? Positive. And then from the y-axis to the orange resultant vector, that would be theta 2, and that would be what sign? Negative, because it's going in the clockwise direction. So we can figure this out. We can figure this angle out. We can figure either angle. It doesn't really matter. We're going to start with theta 2 because it's going to be easier to see. And you can figure it out three possible ways, now that you know this length of this line. So to do this, we're going to use SOHCAHTOA. SOHCAHTOA, right? This is sine, cosine, tangent. So if I want to figure out the theta 2, I need to have, again, O is for opposite. So if I think about my angle, here is my opposite. So in terms of this theta 2, this is my opposite. And then this is the adjacent line. Okay, while this is always my hypotenuse. So C is hypotenuse, and A and B, it's irrelevant because we're using Pythagorean theorem. But again, it's adjacent, opposite, hypotenuse, okay? For this, and we can see that this is opposite of theta 2. So what we're going to do is we're going to look at how do I solve for that angle? Well, we always have our trigonometric function. So we can say sine of our angle equals opposite over hypotenuse. Cosine of our angle is equal to adjacent over hypotenuse. And tangent of our angle is equal to opposite over adjacent. So this is how you get your angle if you knew your opposite and your hypotenuse, or your adjacent hypotenuse, or opposite and adjacent. So for instance, if I was looking for the angle, sine of theta would equal, let's say in this case, opposite and hypotenuse would be our 7 meters over our 7.62 meters, right? So what I would need to do is I would need to say I would need to actually go back and say, okay, well, because I'm saying the sine of the angle is this ratio, I need to figure out how to get there. So again, let's say the sine was 85 degrees. Well, it would give me a ratio where I said 85, I said sine, give me a ratio of 0.996. Well, what's our ratio here? Our ratio is 7 divided by 7.62. The ratio is about 0.91. So maybe if I did sine of 80 degrees, let's see, 0.91. That's not right. How about sine of 75 degrees? That's 0.96. So this is the sine of like 70 degrees. That's 0.93. How about the sine of 65 degrees? That's roughly 0.1. So roughly about, what was it, 65 sine? Roughly about 65 degrees. Let's go figure this out. So if I come back over to here, okay, oops, I need to come back and erase that. Okay, so in order to figure out the sine of theta, we really need to say the inverse sine of 7 over 7.62. Let me erase that and draw that a little cleaner so you guys can see that. So it's going to be the sine, or the inverse sine, excuse me, of 7 divided by 7.62, and that's going to give me my theta. So let's look at that. Let's do the calculation. So I say 7 divided by 7.62, and I say the inverse sine. So shift, and notice I have the inverse sine up here. It's about 66 degrees. So it's pretty close. We were looking at 65 earlier. So it's really, theta ends up being 66.73 degrees. 66.73 degrees. And that's how you figure out your theta, okay? Let's look at doing it with the cosine. Let's see if we get anything different. So I'm going to move this down to here so we have that out of the way. I'll come back and say theta here. Okay, and we're going to be looking for theta 2 every time, okay? So now I'm going to look at the cosine of theta equals my adjacent, which is 3 meters, over my hypotenuse, which is 7.62, which means my inverse cosine of 3 divided by 7.62 is going to equal my theta. Therefore, theta equals, let's look again. So 3 divided by 7.62 equals, and I'm going to do the inverse cosine this time. And that's, again, the same number, roughly. There's some rounding errors going on. So 66.82, 66.82 degrees. Now, again, that's because we're rounding off the 7.62, whatever it was, meters, and that's why we're getting some difference. And then we'll do the tangent. So now it's going to be the tangent of theta is my opposite over my adjacent. And this should be the most accurate because I'm not rounding anything else. So 7 over 3, that means the inverse tangent of, of 7/3 will equal my theta. So now theta equals, and let's go back over to here, and we're going to say 7 divided by 3. Okay, and we're going to say inverse tangent. Again, the -1 shows the inverse. Again, 66.8. So the most accurate number, because we didn't round the 7 and 3, it's 66.8 degrees. 66.80 degrees. Now look, when you're looking for this theta, again, you have to decide how am I going to get the most accurate number. And again, if I've got these solid numbers here that haven't been rounded, these whole numbers, those are the ones I want to use. And because I have the opposite and adjacent, most of the time in this case, a case exactly like this, I would use tangent versus trying to use the hypotenuse number, which has been rounded. Okay, so you can do that. Now you can also solve for theta 1. Well, theta 1 is simply 90 degrees minus that theta 2. Okay, you can also say, well, hey, wait a minute, I could do the exact same triangle where now it's this length, my adjacent is my 7 meters, and my height, my opposite is 3 meters. And you can do the exact same process like that. So what I want you guys to do is I'm going to give you some problems. I'm going to have you solve them. And I want you to solve for a couple. I want you to solve for a couple of the thetas and a couple of the displacement vectors.